So we're talking today about properties of gas. We're jumping into chapter 10. Here's chapter 10. We're in it. Okay. And for the next several chapters. Awesome. Are you inviting us? Nobody else would do that. So now I don't feel special. Anyway, we're jumping to chapter 10. For the next several chapters, we're looking at states of matter in general. What is a gas? What is a solid? What is a liquid? You've known what a gas, solid, and liquid are since about first grade, but now we're looking at them with regard to their chemistry and how their chemistry is affected by the state of matter. So it gets a little bit more complicated. And just in case by the end of chapter 11 and 12 you still aren't sure what a solid, liquid, and gas are, we'll hit them again in physics. So it's okay. This is coming back and back and back in your life. Take a moment and write that down. That's Justin Ortal. Okay. Most of the properties of a gas can be explained by the kinetic-molecular model of matter, which you met in your freshman year during physical science. And it was touched again briefly in biology's little quick picture of chemistry. But most of matter is stuff moving, particles in motion. And the faster they move, the more thermal energy they have, and the further spread out they tend to be, one particle to another. So a gas is the most spread out form of matter that you will casually encounter. There is plasma, which is another form of matter, but you almost never encounter that in your normal life. So we don't talk about it a whole lot in high school. But gases are the most spread out of the three common states of matter. Gases will spread out to fill their container. So there is carbon dioxide and nitrogen and oxygen and trace other gases in the room right now. And it's not like we have a pocket of oxygen floating around and a pocket of nitrogen floating around, and you hope that you happen to take breath when the oxygen is around your head. The gases uniformly spread out to fill their container. So in this room, any point you sample the air is going to be relatively equal amounts of oxygen, carbon, nitrogen, etc. So they spread out to uniformly fill their container. Fluidity, gases behave like a fluid. Gases are a fluid. The word fluid includes both liquids and gases because they behave so much like each other, with the exception that fluids don't float up to the top of their container. Fluids fill their container completely in the bottom, but they don't fill the top. That's the difference between a liquid and a gas, basically. But you can pour gases, you can compress gases, you can analyze gas motion, like you can analyze fluid motion. And a bunch of you are smirking because I'm talking about moving gases. Not everything in the world is about your parts, right? A little bit of. Gases are compressible, okay? Because they have so much space between their particles, you can squeeze a gas and you can make it take up less space. And then when you stop squeezing that gas, it expands. So, for example, I'm going to take a balloon here.
Oh gosh.
Oh no. Are you going to pop it? Okay. I have a balloon, and this balloon is full of gas particles. But I can hug the balloon down, and I can make the balloon smaller by squeezing on it. And that ability is only because there is space between the particles of the gas. If I had a balloon full of water, I couldn't squeeze on the balloon and make it any smaller because there's not enough space between the particles of the water. Liquids don't have enough spaces to be compressible. Gases do. And then once the gas has the opportunity to expand, it will. And so now all the gas comes out of the balloon, goes into the air, and it's like, oh. And it spreads out and takes up much more space because it is able to fill the room, right? So gases are compressible. Gases exert pressure on their containers. So again, air in the balloon, there is pressure on the latex of this balloon that is caused by all of the molecules of the gas bouncing off of the walls of the balloon and off of each other. And their collisions with the wall of the balloon push the balloon out. And so the reason that there's pressure on this balloon is because they are pushing on their container. Gases exert pressure. Liquids also exert pressure. That's one of the ways that they're the same. Gases, though, you can affect that pressure by things like temperature and volume and things of that nature. Liquids, the pressure tends to be only a function of depth and how deep down that liquid is. It is directly related to temperature. If I increase the temperature of this balloon, the pressure in it will go up, which means that if the balloon can stretch, it will. So I could take a blow dryer and blow dryer all over the balloon and heat the balloon up, and the balloon would actually get bigger. Or, I don't have a blow dryer. Or I could take liquid nitrogen and pour it on the balloon would get really cold and shrivel. So, directly related to temperature and inversely related to volume. The more volume that the gas has to expand into, the less pressure there is. So there's more pressure in this balloon right now than that same amount of gas is pushing on the walls right now, because that little bit of gas went into the room, big volume, small pressure. Same amount of gas, small volume, more pressure, okay? So gas pressure is something that you've already heard about. You've already met Charles' Law. You talked about this at length in physical science. You took like a week on Charles' Law. So Charles' Law, volume and temperature are directly related by this awesome equation. Volume 1 divided by temperature 1 equals volume 2 divided by temperature 2. So as the temperature rises, the volume also has to rise to maintain equivalence. So picture this, you've got like 12 liters of gas. So the volume is 12 liters. And the temperature is 100 Kelvin. And so the ratio 12 to 100 is on that side of the equation. Now, if I cut the temperature in half and I go from 100 Kelvin to only 50 Kelvin, this has to stay equaling the same thing. So 12 divided by 100 is the same thing as 6 divided by 50. So in order for these two fractions to remain in equivalence, then the volume and the temperature have to go up or come down at the same ratio so that they are maintained in equilibrium, right? So volume and temperature are directly related. And that was Charles' Law. You should remember that. That should not be a learning moment. That should be, oh yeah, I remember the story of that crazy Charles guy who was a balloonist and didn't know why he floated. Yes. And so he did those experiments. Jacques Charles was also the guy who discovered the value for absolute zero and named it after his friend and mentor, Lord Kelvin. So that's why we got 0 degrees Kelvin as the absolute value of zero. So Jacques Charles, interesting guy, important guy in physics. Here's an example. This is that balloon example I gave you, a balloon filled with a volume of 0.75 liters at a temperature of 25 degrees Celsius is rapidly cooled with liquid nitrogen to a temperature of 0 degrees Celsius. What's the new volume? So here they're pouring liquid nitrogen over a balloon. Here's my equation, V1 over T1 equals V2 over T2. First thing we've got to do is always, 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 Charles' Law and any of these gas laws are worked in kelvins, not in Celsius or Fahrenheit. So if you get numbers in Celsius or Fahrenheit, you have to go in Kelvin, which you need to remember how to do from the depths of your past. Very simply, take any degree in Celsius, add 273, and you're in kelvins. So 25 degrees Celsius is 298 Kelvin. 0 degrees Celsius is 273 Kelvin. So there's my new temperatures. I'm going to go ahead and plug in my numbers. 3/4 of a liter, 298 Kelvin, 273 Kelvin. Now I just have to solve for V2. And so what is V2? We have to solve for the new volume. The easiest way to do that is to cross multiply and divide. So 0.75 times 273, then divided by 298, and I get my answer of 0.68078 liters. So it went from 0.75 liters to, it went down in volume to 0.68078 liters, but that's not right for significant digits. So I have to have my final answer of 0.68 liters, okay? So the balloon shrank 0.07 liters, or about 9% of its volume was lost with a drop of 25 Kelvin in thermal energy. So room temperature to much colder than room temperature, and it lost quite a bit of its volume. So you can see Charles' Law in work. You guys remember Charles' Law? Yes. Renee is saying yes. Praise the Lord. Does Cody remember Charles' Law from physical science? Go, Mr. Wong. Already. Cool.
Yeah.
Boyle's Law is the other one that you learned. Boyle's Law, also a physical science concept you spent a long time on. Boyle's Law, volume and pressure are inversely related. So here, pressure 1 times volume 1 equals pressure 2 times volume 2. As pressure goes up, volume has to go down to maintain equivalence. So again, let's pick some easy numbers to work with. Let's say that this is 12 psi and 5 liters of gas. 12 times 5 is 60. And now let's say that we decrease the pressure from 12 psi down to 2 psi. Well, this still has to equal 60. So that means that my volume has to have responded and gone up to 30 liters, right? So in order to keep this equivalence, if one goes down, the other has to go up. And that was done by Boyle. Volume and pressure are inversely related. He did all kinds of things with cylinders, and he stacked weights on top of a piston and drove the air down and looked at how compressed the air got, a certain amount of force on it. Very cool experiments. You talked a lot about it in 9th grade. Hopefully you're blowing the dust off of that file in your brain and going, oh yeah, I remember Boyle's Law. Well, I'm glad you do.
Is that you?
No,
What?
that is not me. Okay, anyway. A diver with a total lung volume of 1.35 liters takes a deep breath, filling his lungs completely, and then, because he is absolutely stupid, swims up from a depth of 40 meters, a total of 5 atmospheres, to the surface without exhaling. What happens to him?
Die.
Yes. If you have ever been scuba diving, the #1 rule of scuba diving so you don't die is you never hold your breath. And you definitely never hold your breath while you're going up, because the air in your lungs is going to expand as the pressure comes off of your body as you go up. So my dad had one of these unfortunate circumstances where we were down at 110 feet looking at a shipwreck, and he got freaked out. He kind of lost his cool, and he decided he was out. So he just swam to the surface, kicked as hard as he could, and swam as hard as he could to the surface. He was thankfully breathing. He wasn't holding his breath. But when he got out of the water, he was going so fast that he actually breached. The people from the dive boat watched him like leave the water and land. So that was the last time he was diving with me. But he didn't have any of the problems we're about to see that this guy will have, because he, in his panic, did remember to keep breathing and letting that air that's expanding come out your mouth. This guy, dumber than a rock, holds his breath and swims to the surface from 40 meters down. Let's see what happens to it. So 5 atmospheres of pressure is what he starts at, okay? And by the way, it doesn't matter what unit of pressure you use, as long as you use the same unit of pressure over here. So you could be atmospheres, pascals, bar, millimeters of mercury, pounds per square inch, whatever you want, as long as you use the same unit on both sides. So he's at 5 atmospheres at depth, and he takes a deep breath, 1.35 liters of air at 5 atmospheres. That's what he holds his breath at. Then he swims to the surface where there is 1 atmosphere of pressure. What happens to the air in his lungs? So we just solve for the unknown volume, starting by getting a product for the node side. So 5 times 1.35 is 6.75. And then we divide by the 1 atmosphere to get the unknown volume. So his lungs go from 1.35 liters of air to 6.75 liters of air. He explodes is the answer, right? It would be the last dumb thing he ever does. So the air in his lungs went from a volume of 1.35 liters to 6.75 liters. While it's highly unlikely that anyone would resist exhaling during ascent, not blowing out enough air is the single most common diving accident. People who don't exhale enough while they're surfacing don't actually boom, right? But they do rupture portions of their lung. And these poor blokes just had that happen to them. So, yeah, scuba diving generally is safe as long as you're not stupid. There you go. Another gas law. This one is by Gay-Lussac. Gay-Lussac law. Gay-Lussac gases, yes. And he related temperature and pressure. So again, this is another physical science thing. This is all review today. You've had all of this before. Pressure 1 divided by temperature 1 equals pressure 2 divided by temperature 2. As temperature goes up, if volume is held constant, pressure will go up to maintain equivalence. So again, this is like Charles' law, where it's a division, and so they're directly related. If P gets bigger, T has to also get bigger so that the division means the same thing, right? So again, this is equivalent fractions. 2 divided by 3, if we had 2 atmospheres of pressure and 3 Kelvin, wow, that's really cold. And then we were to take that pressure and we were to increase it to 20 atmospheres, and we held everything else constant. This got multiplied by 10, so this would have to get multiplied by 10, so then we'd have a temperature of 30 kelvins, right? So as this gets bigger or smaller, the other term has to get bigger or smaller as well. They have to work together to maintain equivalence. So Gay-Lussac, temperature and pressure. This is why if you take, and actually I think I have a picture of this coming up. If you take a can of soda, dump the soda out, put water in it, boil the water in the can. So set the can of soda on your burner. When the water is boiling, use tongs and tip the can upside down into ice water so that it rapidly becomes cold. The can crushes. And because the pressure inside the can drops and the can can't withstand it, and the atmospheric pressure crushes the can. So kind of cool. I think I have it here. If I don't have it here, I definitely have it as a menu video that you can watch. It's a cool demonstration. I do have it as a can here. There you go. I'm going to pause my recording. Okay, the combined gas law. So this takes Charles and Boyle and Gay-Lussac and throws them all into a paper bag and shakes it up and comes up with one law. So if you remember Charles' law, it's volume and temperature. If you remember Gay-Lussac's law, it's pressure and temperature. If you remember Boyle's law, it's pressure and volume. So I've stuck pressure next to volume, divided both of them by temperature. I've combined Charles, Boyle, and Gay-Lussac, and I have now the combined gas law. And this law will help you calculate changes in pressure, temperature, and volume between two states of a gas. So if you take a gas and you squeeze it and heat it up, what happens to the pressure? Or if you take a gas and cool it down and let it expand, what happens to the pressure? This gas law is the most useful one of all of them because you can see that all three kinds of manipulations are able to be calculated here. Okay, so the, I thought I had an example. I don't have an example. But you can see Boyle, Charles, and Gay-Lussac, all three of them in this equation. Okay, so this will be your friend. You will use this a lot. Hello, friend. The last one I have for you is Dalton's law of partial pressures. All of the pressures of individual gases equal the total pressure of all gases in a container. So we started by saying that in this room there is some carbon dioxide, some nitrogen, some oxygen, and some other little gases, some other trace gases that are also floating around. If I were to measure the air pressure in here right now, the air pressure in this room, right around 1 atmosphere because I'm not too far off sea level. That's the total air pressure in the room, okay? And then I were to calculate how much of the air pressure in the room is provided by just the nitrogen in the room. I would get some fraction of an atmosphere. And nitrogen in this room is some partial pressure of the total air pressure in the room. And then if I were to calculate how much pressure is being provided by oxygen, I could add that to the nitrogen, and I would have, you know, another fraction of the total air pressure. And then I were to calculate how much pressure is being provided by the carbon dioxide. I could do the same thing. And I could keep going to all the trace gases that are in the room. And if I could calculate how much pressure is being provided by all of these gases separately, I could then add up all of those pressures and tell you what the air pressure in the room was. Or other way around, I know what the air pressure in the room is. I know how much pressure nitrogen and oxygen are providing. I can calculate how much pressure carbon dioxide is providing. So it's the law of partial pressures. All of the pressures of the individual gases add up to the total pressure of the gases in the container. You won't actually do a whole lot of manipulation with this because in our high school lab, we don't have the apparatus that it takes to measure partial pressures. But just know that mathematically it's possible. Okay? You can add up partial pressures. And I don't know if I do the ideal gas in this lecture. No. Okay. So this is just, again, showing you the partial pressures here. So if I have 0.6 of a mole of hydrogen vapor, and I have 1.5 moles of helium, I can calculate what the pressure of that gas is here at the 0.6 of a mole of hydrogen at 20 degrees Celsius is going to provide a certain amount of pressure. 1.5 moles of helium at 20 degrees Celsius is going to provide a certain amount of pressure. And then I can calculate the pressure in the entire container by adding those two up. And I could predict what the pressure in the container will be if it has those two gases in it. Okay? And across the top, it does the arithmetic for you. So, let me move my picture. 2.9 atmospheres of pressure provided by the hydrogen, 7.2 atmospheres of pressure being provided by the helium. So the grand total would be 10.1 atmospheres of total pressure in the container if you added up the hydrogen and the helium. Okay, it's just straight up addition. And I think that's it. Yes, that's it. Okay. So that's a lot of information, but it's all stuff you've already had before. Do you have any questions? Do you remember these things from physical science? Yeah. Abraham does not. He's got the smile on his face like I've never seen this before. Well, you should have taken Mr. Wong's physical science. Anybody else? Hi, Renee. That's for nature.
Hey, Miss Sally, do you watch these before you post them?
No.
You post them?
I just posted.
He's like, I'm gonna